On to exponential and logarithmic functions. Exponential functions are functions of the form where you have some real number different from 1 as the base, b, and x appearing in the exponent. So your dependent variable, or sorry, your independent variable is appearing in the exponent. Couple basic properties of exponential functions is that the domain is all real numbers. Okay, range has to be all numbers greater than 0. Okay, so if you think of everything above the y-axis or x-axis, sorry, and the graph of the function must pass through 0, 1. That's because laws of exponents say that if you have anything to the 0 power, you always get out 1. Okay, horizontal asymptote at y is equal to 0 as well. As I mentioned before, properties of exponents still hold with all this stuff, so please review those if you are a little rusty on that. Now, at the same time as we define exponential functions, we're going to define logarithmic functions because they do go hand in hand. Logarithmic functions are functions of the form log base b of x. B is called the base, again, number greater than 0, but different from 1. That's because if we have a log base 1, everything kind of collapses on itself, mainly because we'd have, well, we'll get to that in a minute. But logarithm essentially was created as a way of defining the inverse function of an exponential function. Now, inverses we'll get to in a later video, but just kind of a prelude to that. One of the important ideas, though, with logarithms and exponentials is to be able to go through this back and forth movement. So if we start in logarithmic form, we should be able to convert it over to exponential form and vice versa. Okay. Notice that b is still the base, so the b remains the base of the logarithm and is still the base of the exponential form. But then if we look at where the x's are and also where the y's are, they switch, right? One property of inverse functions is that the domain and range values switch. So whatever the input is in the logarithmic form, in its inverse function, it needs to be the output. Okay, and vice versa for y. Okay, and then we have a couple names for special logarithms. If b is equal to 10, then we call that the common log, and that's just written as log, no base. It's understood to be base 10, and then the natural logarithm has a logarithm of base e. And e, just as a refresher, we can say that's approximately 2.71. If you use a scientific calculator, e is programmed into all of them. So now we're just going to go through some quick examples of logarithms. So here, if we want to evaluate these logarithms, I don't know what these are equal to, but I do know, well, I can call it some value x, and then I can find the value of x later on. What I want to remember, though, is this is in logarithmic form. I don't know what it is currently in logarithmic form, but I do have a way to express it in another form. I can express it in exponential form. So if I want to, I can change this from logarithmic form into exponential form. So the base of the logarithm is still the base of the exponent. And now I have to figure out what goes up here and what goes on the other side of the sign. So here, the output is x. That becomes the input in the exponential expression. And then 81 is the output. So now I need to think 3 to what power is equal to 81? Well, x is actually going to equal 4. Okay, so 3 to the 4th is going to equal 81. But another way that I could see this is I could represent 81 as 9 times 9. I know that. Okay, but then each 9 is really 3 squared. Okay, and using laws of exponents, that's 3 to the 4th. So I can just say x is going to equal 4. And I'm done with that problem. A couple other interesting problems. Here, I'm going to apply the same technique, set this equal to x, and now I want to say, well, this is the same as saying 1/4 to the x power is equal to 64. Okay. Laws of exponents say, well, if I have something in the denominator, I can bring it into the numerator and just change the sign of the exponent. So this is really the same as saying 4 to the minus x is equal to 64. Let me erase that. Okay, so 64. 64 is 4 to the third, so I have 4 to the minus x is equal to 4 to the third. And then solve for x, and I'm eventually just going to get x is going to equal minus 3. Okay, I filled in, I skipped a few details, but essentially the idea that I'm trying to use is up here, I got it so that the bases were the same. Okay, if the bases are the same, and actually the same thing down here, if the bases are the same, then the exponents must be the same. So x is 4, and then minus x is minus 3. Do some algebra, divide by minus 1, you get x is minus 3. Okay, last problem. We have log base 256 of 4 is equal to, oh, and I have the wrong pen, is equal to x. Okay, so I'm going to write 256 to the x power is equal to 4. Okay. Oh, well, let's see. Now I have to probably play with my calculator a little bit, but I know that 256 is 16 squared. Okay. And then I can use laws of exponents, multiply. But 16 is 4 squared. So 4 squared to the 2x is equal to 4. Okay, and I'm going to come up over here. Laws of exponents, again, multiply the exponents together. 4 to the 4x is equal to 4. Divide by x, or again, same bases. So the power should be the same. 4x is equal to 1. X is equal to 1/4. Okay, and that's a couple quick examples of how we can go between logarithmic form and exponential form. Okay, and just as we've been using laws of exponents over and over and over, logarithms have special properties with them as well. I call them log laws, just because it's fun to say. But there's 3 properties, and then kind of one that's more of a, not definition, but it follows from these other properties. So the first one is a product to sum law. Essentially it says if you have the logarithm and the input is a product, so if you express the input as 2 numbers or 2 values multiplied by each other, you can break that up into a sum. Okay, so notice that if you have a product inside, break it up and it becomes a sum of 2 logarithms, and the base stays the same. Whatever the base was before, it stays the same after. First property. Second property is the quotient to difference law. So if you have a logarithm of a quotient, so something, logarithm of 2 values divided by one another, that is equal to the difference of the 2 logs. Now, one very, very common error here is to mistake this with saying this is log base x of a over log base x, and I should put this in parentheses, b. Okay, these are not the same, and in fact if you look a little bit further down, this is equal to something completely different. Okay, last log law is the power law, and that says if you have a logarithm of an exponential expression inside, this really just comes down in front, so it becomes y times log base x of a. Okay, these 3 properties, and and then the change of base formula. This is where I was kind of going with this before, but essentially you can change it to whatever base you want. I personally like natural logs, but if you have log base a of b, change it to whatever base you want. So for example, down here, I could write this as log of 6 over log of 2. And remember, if I don't have a base here, that means log base 10. And I can compute that, but I can also do natural log of 6 over natural log of 2. Okay, and I should get the same thing. And if I punch this in my calculator, I should get out 2.58496. Okay, basic run through of exponentials and logarithms. In the next section, we will start solving equations involving exponentials and logarithms.